Solubility Equilibria, I am going to be using this set of notes over here by Mr. Lim Jin Yang. Unfortunately, because it was created by him and is his intellectual property, I'm unable to provide a publicly available copy of this particular set of notes. But basically, all of these exercises are just the same exercises as in the HCI lecture notes. So, and the class exercise, there isn't a soft copy of that anyway that's available to students like myself. So, just going to be running through this template and also some of the pointers here, and we're going to go through some of the class exercises in solubility equilibria. Okay, so in order to calculate KSP from concentrations and vice versa, you will need to be able to have in mind this particular mental flowchart for problem solving, and I think this flowchart is in your notes as well. So I'm going to color code each step so that you understand better, okay? If the question is kind enough as to give you the solubility in mole per dm cube, then you don't need to go through this step here. You can just go from here to KSP. And I've chosen to start the video here because I trust that you already know how to write the KSP expression. And if you don't, you can learn it more or less in 30 seconds just by reading the HCR lecture notes. So I don't think there's much to go through in that aspect, okay? So in order to find KSP given solubility, we need to be able to convert grams per dm cube to mole per dm cube. So in order to do this, we need to consider the MR of AgCl, which is given to us here at 143.5. So if we want to find solubility in mole per dm cube, let's use S to denote solubility, okay? So solubility, if I want to convert the units from grams per dm cube to mole per dm cube, this is going to be, I'm given 1.46 times 10 to the minus 3 grams per dm cube, right? And then I'm going to divide it by the MR. So the MR, I'm given 143.5 here. So if I actually compute that, I should be able to get a solubility in mole per dm cube. I should have put this in orange, sorry. So if I convert grams per dm cube to mole per dm cube, I should get a value of I should get a value of 1.017 times 10 to the minus 5. Stick to the units moles per dm cube. Okay, so at this point, by converting it to moles per dm cube, this is because, right, in my KSP expression is going to have the concentration, its concentration terms, all right? And each of these concentration terms of the ions are in mole per dm cube. So in order to find the molar concentration, I must first convert the units of solubility from the conventional units of grams per dm cube into mole per dm cube for the purposes of my calculation. Okay, now it helps to write out the equation for the dissolution, even though it's not required. And even though in this case AgCl is quite a simple salt, but I still find that it's good practice to help you and guide you along. So if we write the equation for the dissolution, AgCl solid is going to dissolve in water. Do note that this is a reversible equilibrium. That's why we have this KSP in the first place. So when you have chemical equilibria in chapter 7 or now in solubility equilibria, or next topic, chapter 14, acid-base equilibria, you are dealing with reversible reactions, okay? So please don't forget your reversible arrows. And this is going to be Ag plus Cl minus. So I go from an ionic solid into aqueous ions, okay? And the KSP, okay, in this case, is going to be, if you look at this, because the concentration of AgCl, okay, we have found is this orange term, right? So in that case, if I want to find the concentration of the ions, what is going to be the concentration of Ag plus aqueous? Obviously, in this case, it's just going to be the same as the concentration of AgCl. So this is just going to be, make sure you have the correct KSP expression. Then you can sub in, this is actually just going to be the same as concentration of AgCl. And then because the concentration of Cl minus is also this value, you can just write a squared. So KSP is going to be equals to, if you clear your scientific calculator, you should get 1.04 times 10 to the minus 10. And how we determine the units of KSP is similar to how we determine the units of KC back in chemical equilibria. So because I have mole per dm cube times mole per dm cube, my units are going to be mole squared. And then per dm cube becomes dm power negative 6. And that's it. Okay, so this is a relatively simple example. But then you also need to be able to do the reverse. So this is exercise 4.2 of the HCA lecture notes. And it talks about MgOH2. So now it's a bit different. Pay attention to this, okay? It says that you want to, they give you the KSP and you want to find solubility given KSP. So let us first write out the equation for the dissolution. So I go from a solid, salt, make sure the formula is correct. Once again, this is a reversible reaction. That's why we're dealing with an equilibrium here. And this gives me aqueous Mg2 plus, but it's going to give me 2 OH minus. And this molar ratio will be important later on when we are determining molar concentration of ions. So in order to do the reverse, it's not as straightforward as we're doing the forward. We need to use an algebraic method. So pay attention, this algebraic method involves letting an unknown quantity S be the solubility of MgOH2. In this case, this S is actually the solubility in both mole per dm cube and grams per dm cube. So I don't think I should highlight it in blue. It's just the units of S. So if you look, right, KSP, okay, is going to be, let's just write out the KSP expression. So I want to find the molar concentration of ions. I am going to have, this is going to be Mg2 plus. And by the stoichiometric ratio, the KSP expression, this is going to be OH minus, and there's going to be a power here, right? It's going to be OH minus squared. So if I let S be the solubility, then what is going to happen is this is going to be S times 2S squared. And we are given that this is 6.30 times 10 power minus 10. Okay, now why is this the case, people? Because if you think about it, the solubility is just when I dissolve a certain amount of MgOH2 in water to form an aqueous solution. What is going to be the molar concentration of free aqueous ions in this solution? So if S is going to be the solubility, S is the concentration of ions, correct? So the concentration of Mg2 plus is going to be S. But the reason why I have 2S here is because for every mole of MgOH2 that dissolves in water, I form 2 moles rather than 1 mole of free hydroxide ions in aqueous solution. So if you solve this algebraically, it's not that difficult, it's just an algebraic method. We're going to get 4S cubed is equals to 6.30 times 10 power minus 10. And please just press your scientific calculator, the polynomial solver, to find this. This is going to be... I don't think I need to teach you how to press your SC, right? In any case, if you don't know how to solve polynomial equations using your SC, which, by the way, you should, you can just use your GC. Your GC is allowed in the chemistry paper, by the way. So that's going to be 5.40 times 10 to the minus 4. And this is the concentration in... this is the concentration in mole per dm cube. So if I dissolve 1 mole of MgOH2 in water, I'm going to get this S, 5.40 times 10 to the minus 4 mole per dm cube of free Mg2 plus aqueous ions. Okay, so this is one done. Now I need to find it in grams per dm cube. So I am given MR is 58.3, right? So now I'm just going to do the reverse of that conversion I showed you earlier. If I want to convert this to... if I want to convert this, the units of S, from mole per dm cube to grams per dm cube, then that is just going to be, I have the concentration in moles per dm cube, and then I'm going to multiply it by the MR, which is given to us 58.3. So if you just do this simple math, you should get a value of 0.0315 grams per dm cube. So I hope this conversion makes sense to you. If you need to pause a bit and comprehend the algebraic method further, you may. If you want to scroll up and take a screenshot of this flowchart, you also should actually, because this flowchart is very, very useful as a problem-solving guide. So please have this flowchart in your mind every time you're doing problems in solubility equilibrium. Okay, so this is the first important type of calculation in this topic. The other one is ionic product. So you remember in chemical equilibria, we talked about the concept of QC, right? So in chemical equilibria, I said that my reaction quotient QC is just going to be, let's say I have A plus B. This is a reversible reaction. C plus D are the products. Okay, so this is an equilibrium. Now remember, if I write my equilibrium constant Kc, I'm looking at the equilibrium concentrations of everything. So equilibrium concentrations of the products, of course, raised to the appropriate power depending on the stoichiometric ratio. And then these are all the equilibrium concentrations of the reactants, right? But if I'm looking at QC, the reaction quotient, instead of the equilibrium constant, I'm interested in all of this. But notice I don't write the subscript. Why? Because all of these people are instantaneous concentrations. So intuitively, if the instantaneous concentration of the products is higher than the instantaneous concentration of the products at equilibrium, is my reaction going to proceed in the forward or backward direction? In other words, what is the position of my equilibrium? So go back to your chapter 7 on chemical equilibrium now. If QC is greater than Kc, it means that the concentration of my product is higher than it should be. So in order to achieve equilibrium, in order to achieve dynamic equilibrium, you need to proceed the reaction in the backward direction, which means that the POE is lying to the right. So therefore, the system will favor the backward reaction by Le Chatelier's principle to re-establish equilibrium. Okay, then of course, if QC is equals to KC, then everything is well and good. The system is at equilibrium. On the other hand, if my reaction quotient lies less than the equilibrium constant, this means that the concentration of my products is less than it should be at equilibrium. So this means that the position of equilibrium, if I want the reaction to proceed in the forward direction, it means that POE must lie to the left. Okay? Understand? So this ionic product, as Mr. Lim's notes have pointed out, the concept is quite similar to that of QC. So IP has the same expression as KSP, except that in KSP, these concentration terms are equilibrium concentrations. For ionic product, these concentration terms here are instantaneous concentrations. Okay? If you need time to digest, please go back to your chapter 7 notes in order to better appreciate the concepts of dynamic equilibrium, position of equilibrium, all that. But assuming that you have a good grasp of that chapter, let us go on now to ionic product. So, once again, we have three possible scenarios, just like in Kc. So if Ip is less than Ksp, it means that no precipitation occurs. If Ip is equals to Ksp, the position is at equilibrium, and so therefore the first trace of precipitate just appears. So this will be the phrasing. The question will say something like, calculate the concentration of something, something, something such that a precipitate just appears. That's Ip equals to Ksp. Okay? And Ip will, and precipitation will definitely occur if Ip is greater than Ksp. Okay? So let us go on to calculating if a salt will precipitate. So this is a modified version of exercise 5.1 from the HCI lecture notes, but I want to go through this in detail because there's a couple of traps. Okay, so you are given the KSP and you are asked to determine if a precipitate forms. So this means that you need to calculate, you are given KSP. So in order to determine if, 如果, if a precipitate forms, you are going to need to calculate IP and then determine, based on the red box or dot, which of the following three scenarios it is, and then therefore if precipitation will occur or not. But in order to determine IP, okay, I need these instantaneous concentrations. That is the main focus of what we're going to calculate. How do I calculate the instantaneous concentrations of all of my ions? So, first things first, okay? I want you to read this question very, very carefully. And then I want you to tell me, pause the video and think for yourself, what do you think is going to be the instantaneous concentration of Ca2 plus based on this information? I'm not sure if you spotted that trap or not, but notice these three words here. An equal volume. Because what you notice, right? In order to calculate instantaneous concentration, I need to number of moles over volume, right? But they haven't told you what volume of each of these two solutions is mixed together. They just tell you the concentration and then they say that it's an equal volume. So this means, right, that actually at this point, my instantaneous concentration of calcium ions is actually, I don't need the volume at all. I only need the relative proportions. So if initially in the initial solution of Ca2 plus, I had 1.00 times 10 to the power minus 3 mole per dm cube of Ca2 plus. But then now if I mix it with an equal volume of something, it means that what am I doing to the volume? I am doubling the volume. Understand? So if I double the volume, this means that regardless of what the initial or final volumes are, doubling the volume just means that the concentration will be half. So I actually don't need to know what the exact volume is. I just need to know that I need to divide by 2 because concentration is halved because volume has doubled. Understand? So this simple division is going to give you 5.00 times 10 to the minus 4. And what do you notice? The same can be said for SO4, right? Because SO4 is also this concentration, is also added to an equal volume. And so therefore, this is also going to be the concentration, the instantaneous concentration right now of sulfate ions in aqueous solution. So IP has the same expression as KSP, and it's just going to be the instantaneous concentrations. So this is going to be concentration of Ca2 plus. We don't need to worry about the mole ratios in this case because it's just 1:1, thankfully. So this is just going to be 5.00 times 10 to the minus 4 multiplied by itself. So we can just add a squared, and that is going to be, I'll write it on another line, that is going to be, if you press the calculator, you will get 2.50 times 10 to the minus 7. Please put your units. So it's mole per dm cube times mole per dm cube, right? So mole per dm cube times mole per dm cube, I'm going to get mole squared dm power minus 6. And now this is IP, right? I want to compare IP to KSP. So we'll compare with the KSP value up here, highlighted in blue. And you will see that obviously something to the power of times 10 to the power of minus 7 is obviously going to be less than something times 10 to the power minus 5. So because I have established that my ionic product is less than my KSP, in other words, my QC is less than KC, so my position of equilibrium is lying to the left, and therefore no precipitation will form. Because, right, in this case, the reaction, you can think of it as the other way. So instead of, sorry, that's just another example. I'm not going to go through this in this video. It's just I worked it out for myself a couple of months ago. Yeah, but this is just exercise 5.2 in your lecture notes. It's a work example. So you see my very, very colorful working of this example versus you see the not so colorful working in the HCI lecture notes, also not that much difference lah. But basically, in this case, I start, my reactants are the two ions. Okay? And then I am trying to form my CaSO4 salt, right? So this is going to be a solid. So if I want precipitation to occur, it means that I want this reaction to proceed in the forward direction, right? But then, if IP is less than KSP, i.e. QC is less than KC, my POE is to the left. My POE is to the left. That is why this precipitate does not form. Understand? Okay? So naturally, I've shown you an example where the precipitate does not form. Obviously, I also need to show you an example where the precipitate does form. So this is exercise 5.1. 5.2 is the one that is worked out in your lecture notes. Fine, if you want to, you can just pause here and take a screenshot of my colorful working for 5.2 lah. But this is basically just identical to the HCI working, just in color. Why I decided to waste time and resources writing it out, I have no idea. But yeah, you can just take a screenshot if you want. And 5.3 now, okay? So 5.3 is not so kind anymore. They need you to consider the mole ratios because this is CaNO3 to calcium nitrate. So I have two salt solutions. It is added to a solution of magnesium sulfate, and then they give you the conclusion this time. So they say I want a precipitate to be formed, but I also want to know what is the minimum concentration of Ca2 plus. And then once again, you need to calculate IP. They give you already the KSP. Can they technically say, oh, given that a precipitate does occur, find the range of values of KSP? They can, but it's just that I haven't been able to find any questions to show you. If I do, I might edit it onto the back of this video as additional thing, but if I don't, then it means I haven't found. Okay, so if I want a precipitate to be formed, let me just annotate that. If I want a PPT to be formed, this means that at least IP must equals to KSP. Technically, you can also write IP must be greater than or equals to KSP. But in this case, they want the minimum. So I'm solving an equation, not an inequality. I will just write IP equals to KSP. Okay, so my ionic product, okay, is just going to be equals to concentration of SO4 2 minus, in this case, is just the concentration of MgSO4. So this is going to be, no, actually, I'm just going to make it good practice. I'm going to write out the IP expression first. Okay, and then only SO4. So if I want IP equals to KSP, this means that this thing must be equals to 2.40 times 10 to the minus 5, correct? Excellent. And then, if I'm given SO4, I treat this as an unknown. So now my unknown is in green. I'm trying to solve this. Okay, so this one times 2.00 times 10 to the minus 4 is going to be equals to this KSP expression on the right hand side. Okay, and so therefore it's just simple division already lah. It's just going to be this one divide by this one. Oh yeah, minimum concentration of Ca2 plus, which is going to be, if you press your calculator, you're going to get 0.120 moles per dm minus cube. So at this point, IP equals to KSP, a precipitate can be formed. Because if this is in equilibrium, it means that at equilibrium, there is some kind of product being formed. Okay? In fact, I don't want the POE to lie to the right, because if the POE lies to the right, then the product will start being used up. So I don't want that. I just want IP equals to KSP, i.e. QC equals to KC, then only my precipitate can be formed. Okay? Selective precipitation, should I go through selective precipitation? Actually, no, I'm not going to. But exercise 5.4, this is basically just an application of everything you've learned so far. I've more or less just gone through the main types of calculations. But the part that I want to touch on before I go on to the part on complex formation, the part on complex formation, I am going to bring in concepts from transition elements as well. So if you haven't learned transition elements yet, please do not go on to the next video on complex formation. Please just stick to what I'm doing here. So exercise 6.1 will be where I leave off for this video, and that will be all for solubility equilibrium. Complex formation, or that I will discuss with the context of transition metals in mind. Okay, so exercise 6.1 over here talks about the common ion effect. So I don't think the common ion effect is that hard to understand, but basically, right, common ion means that I add some NaCl, right? So the common ion between AgCl and NaCl is just going to be Cl minus. So if I add NaCl, then concentration of Cl minus is going to increase. So by Le Chatelier's principle, when something on the right increases, or rather when the concentration of a product increases, position of equilibrium will shift to the left in order to correct this change and re-establish a new equilibrium. So this means that I'm going to decrease the solubility of AgCl. So I will expect the new solubility, which I will denote using the notation S prime, to be smaller than the original solubility, S. So for exercise 6.1, this is just a very simple extension of, or rather we have seen this type of calculation earlier in the video. They give you KSP, they want you to find solubility given KSP. So if KSP, let us write the KSP expression. KSP is going to be concentration of Ag plus times concentration of Cl minus. And if we write this as solubility, we can write it as S squared, right? So S is the original solubility. S squared, because whatever this solubility in mole per dm cube is, I'm going to, when 1 mole of AgCl dissolves in water, that is how much the concentration of each of these ions is going to be. So that's why it's S squared, okay? And we are given this is going to be equals to 2.00 times 10 to the minus 10, okay? So as a result, I can just solve for S by taking the square root. S is just going to be 1.40 times 10 to the minus 5 mole per dm cube. In this case, there is no need to convert to grams per dm cube simply because they haven't asked you. Okay, solubility. Okay, even though when we learned about concepts in solubility in Sec 1 and Sec 2 LSS, we do think by default of the units of solubility as grams per dm cube. I think the term that you first encountered in Sec 1 was actually grams per 100 grams of water, which I think is even more misleading. But if you think about it now through a more mature lens, you should appreciate that that's just the same as saying grams per dm cube lah. Because per 100 grams of water is just to say per 100 ml of water, which is also to say per 0.1 dm cube of water. Yeah, gets? Okay. I've digressed a bit, sorry. But yeah, even though we tend to think of the units of solubility as grams per dm cube by default, if the question doesn't ask you to change it to grams per dm cube, you can just leave it in mole per dm cube because grams per dm cube and mole per dm cube are equally valid units of solubility. Okay, so this is just to say when 1 mole of this salt dissolves in water, I'm going to get this amount of ions. Okay, so in this case, I'm going to let S prime here in green be the new solubility of AgCl. Or let S prime be the solubility of AgCl in 0.100 mole per dm cube NaCl. So this means that my concentration of Cl minus, right? Now my concentration of Cl minus, okay, is actually going to be this solubility S prime. Okay, because now the new solubility means that when 1 mole of AgCl dissolves, I'm going to get S prime moles of free chloride ions in water. Okay, so this term that I've written down so far, this is the concentration of Cl minus due to the dissolution of solid AgCl. But then I also need to add the concentration of Cl minus due to the presence of this already aqueous solution, which is going to be 0.100 moles per dm cube from the NaCl. Understand so far? So, no, let me write it another way. KSP is still the same expression, right? So it's now Ag plus, concentration of Ag plus, times concentration of Cl minus. So what's the new concentration of Ag plus? It's just going to be S prime, right? and then times this entire expression. So you will see that we actually get a quadratic equation. But the key insight here is KSP remains the same. So this means I'm going to get a quadratic equation, and it's going to be equals to, my KSP is always stayed the same, at 2.00 times 10 to the minus 10. Now, solving of quadratic equations is not required in H2 chemistry. So if you want to just plug this into your scientific calculator or your GC and solve, the examiner cannot fault you. Personally, that's what I prefer to do. But the method that HCI and I think a couple of other JCs will teach you to avoid entirely the need to even key in your GC is to write the following, okay? They're going to ask you to assume, oh dear, they're going to ask you to assume that the concentration of S squared is much, much less than 0.100, such that it's negligible. Okay, so this means that this thing, you can approximate it to 0.100. And if you think about it, this kind of approximation does make sense, right? Because if my solubility decreases and AgCl is already so insoluble, my new solubility, whatever it is going to be so small that this approximation can be valid. So this would mean that you can just write this as, can I use a, yeah. So I'm going to say that this expression is approximately equals to 0.1. So I can write this as simply 0.100 equals to my KSP. And then after that, solve lah. But personally, I don't like to do this. The reason why I'm showing you this method in the first place in the video is because this method of assuming will become very, very important when doing calculations in the next topic on acid-base equilibria. Okay, so this is going to be, if you solve, you're going to get the new solubility will be 2.00 times 10 to the minus 9 moles per dm cube. So naturally, my solubility has gone down from 10 to the power minus 5 all the way to 10 to the power minus 9. And obviously, 10 to the power minus 9 is indeed much, much less than 0.1 because 0.1 is just 10 to the power minus 2. Okay, so I hope I have managed to bring you through some of the key calculations in solubility equilibria. I may or may not do a video for acid-base equilibria. I probably will because it's very high yield, but I'm a bit lazy at this point, so we'll see how it goes. And the last part on complex formation and its impact on solubility, also pH and its impacts on solubility, I think I'm going to touch this page when I am discussing transition elements. And I'm going to touch this page when I'm discussing acid-base equilibria. So the last two pages, KIV for future videos and future topics. Okay, thank you, bye-bye.